Upon popular request, let me elaborate a little bit more on the concept of density operators in terms of how they reflect our knowledge about the state preparation. I guess, as always, the best way is to give you a specific example and elaborate on that example. Let's bring our two heroes, Alice and Bob. And suppose Bob is preparing a quantum object in a quantum state psi k, which is chosen from a set of possible states that he can prepare this object, and he prepares state psi1 with probability p1, psi2 with probability p2, and so on and so forth. So he draws the state from a set of possible state with a certain probability distribution. So of course, Bob knows which particular state he has. So he knows, for example, that this quantum object is prepared in state psi42. But Alice doesn't know this. So all she knows is the general procedure. So she knows that it will be psi1 with probability p1, psi2 with probability p2, psi42 with probability p42. So when Bob sends any quantum object to her, she thinks, well, now I have to make statistical predictions. So if Alice is about to make any statistical prediction, so then she can only attribute density operator to the state of the object that she got from Bob, and that density operator is sum over probabilities pk projectors on psi k. So now Alice is going to use this density operator to make any statistical predictions in her lab. So she will then use quantum rules, and if she wants to measure any observable A, she will then take this particular density operator and will do the calculations with this density operator. So as you can see, it is indeed the case, perhaps, that if Bob picked psi42, then what she really has is a projector on psi42. But as she doesn't know it, she cannot make these assumptions. She makes sort of perhaps lousy statistical predictions using this density operator that reflects her lack of knowledge about the preparation. It may be psi42, but that only can happen with certain probability as far as she's concerned, right? So the real factual situation is that she has state psi42, but not knowing about it, she just quantifies her knowledge on the basis of what she knows about Bob's state preparation. So therefore, it is not this density operator, but this density operator that she's going to use for her statistical prediction. But now suppose Bob says, well, Alice, I was following this procedure, and now I'm communicating to you that the outcome of me sort of preparing this object in a given quantum state was 42, so I'm sending you psi42. And Alice, who trusts Bob, say, well, great, Bob, now I can update my knowledge about the state preparation, so it is psi42. So now I can make sharper predictions, so I can then take this state and do all the statistical predictions using this particular state, because out of the sudden she knows, after Bob communicated to her, that this is actually the state she has. So you can see there's no contradictions between statistical predictions based on those two different density operators. It is just when she has full knowledge about the state preparations, when she knows it's psi42, she can make sharper predictions. And this density operator will give sort of more lousy predictions, so it will be just more vague, and in this particular case she will be much sharper. She can predict certain things with a sharper probability distribution and be more precise in this sense. So as you can see that we have a situation where the density operator can be changed if you receive an extra knowledge about the state preparation. So initially, without any communication from Bob to Alice, Alice has to assume that she has the state rho in this particular density operator, simply because this is how much she knows about the state preparation. But as soon as Bob tells her, well, actually, wait a minute, Alice, I can give you more precise information, it's psi 42. Or he can be also vague. He can give her, say, a different kind of information, say, well, you know, it was psi 42, or maybe it was psi 41, I'm not so sure. So then she has to adjust this density operator. So that's how it works. Now, that is also equivalent to the following situation. You can imagine that instead of Bob sending a quantum object to Alice, prepared in one of those states psi 1, psi 2 till psi n, you can imagine situations where, in fact, they have two entangled objects, so they share one subsystem is with Bob, the other subsystem is with Alice, and the whole thing then is prepared in entangled state psi, which we can write as sum over k square root pk psi k and a certain state from the orthonormal basis bk. And now we can see that we have almost identical scenarios. So Bob, instead of sending an object in a given quantum state, can simply, in this case, perform the measurement in the B basis. A given measurement will just bring a particular outcome. So, for example, when Bob performs the measurements on state B, say that k is 42, right? Our magic number, 42. So in this case, Bob has this state, this object here in state B 42. On Alice's side, he's collapsing using this ugly language of quantum collapse. You know, I cannot stand this quantum collapse. It's convenient. It's convenient mathematical shortcut. So the whole thing is collapsed into B42 psi 42. And all that happens with probability P42, right? So again, after performing this measurement, the real factual state at Alice's location is psi 42. But, you know, she doesn't know the outcome of the measurement, so Bob is not going to tell her what happened, unless he, if he does, if he sort of communicates to Alice and says, hey, Alice, I did this measurement on our highly entangled state. The outcome was 42. So then Alice knows that she has state psi 42. We, of course, assume that they know that they share this particular entangled state. So, but you see, without Bob communicating to Alice the outcome of the measurement, all Alice can say is this. Well, I know that the Bob performed measurement. I know the state, and I know that the outcome could be 1 with probability P1, 2 with probability P2, and therefore I can have state psi 1, psi 2 with corresponding probabilities. That is the state after the measurement, because I have collapse on this product state, like psi 42, B42 in this particular case. So you see, without communication, Alice can, looking at this state, can only assume that, can only associate the density operator, which is just the partial trace over Bob's system. And no matter what you do, you can perform the measurement on the Bob subsystem, you can do whatever you want that has no impact on the state of the system here, unless you provide some extra information. So you see, without any communication, all Alice can do is to just do the partial tracing or think in terms of ensemble. It's only when you add classical communication, when you start talking about the outcomes, and if Bob is willing to communicate the outcome of this measurement, or which is equivalent, if Bob is willing to tell Alice which particular state he's sending to her, then of course then you have to update the density operator. I hope it is clear. You know, it's one of those tricky things that you have to probably think over and over again. If it is not, just do drop me a line. I'll try again. So I'll try to explain it over and over again, because it is one of those subtle things and quite often a source of many confusions. So it's good that you picked it up. I'm glad that someone asked a question about this. I'm very happy to go over this again if necessary.